Each parallelogram has a side that is labeled base. Study the examples and non-examples of bases and heights of parallelograms. Then answer the questions that follow. Examples. The dashed segment in each drawing represents the corresponding height for the given base. So we have a height and a base. 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 Alright. On the non-examples, the dashed segment in each drawing does not represent the corresponding height. So it's not the height. We have a dash, but not a height. Still has a base, still has a base, has a base, has a base, but not a height. Okay? At least that's what it's telling us here. This one here, the base is this little diagonal one there. Alright, so what do you notice here? Well, a couple of things you might notice is that all these heights have what? A little square right there. And what does that square indicate to us? Remember what that indicates? It tells us that it has a 90-degree angle right there. That 90-degree angle is always on where the height and the base come together, isn't it? So where the height and the base meet, there's a 90-degree angle every single time on the examples that are going to work. Over here, there's no 90 degree. There's no 90 degree. There's no 90 degree. Here you might say, well, there's 90 degree. Yes, that's true, but which one do they call the base? They call that line the base. So the 90 degree is not connected to the base, so it doesn't quite work there. Select all the statements that are true about bases and heights in parallelograms based upon what we just saw. Only a horizontal side of a parallelogram can be a base. Well, horizontal, what they're talking about is it has to go this way. When we look over here, is that a base? Yep. Is that a base? Yep. And those are not the horizontal ones, are they? So they gave one example horizontal, but that has nothing to do with it, okay? So that would be a false statement. Any side of a parallelogram can be a base. Any side. That is true. And we see that there's a side there, on the left, up top, to the side. Any side can be a base. A height can be drawn at any angle to the side chosen as the base. Any angle? No. What did we talk about just a second ago? We said nope. It has to be what angle? 90 degrees. If it's going to be a height, it has to be 90 degrees. A base and its corresponding height must be perpendicular to each other. It's a great word. Do you remember what perpendicular means? It means you have a line and it matches another line right here, and where it meets, that place where they meet, form a 90-degree angle. That's perpendicular. So we already said it needs to be 90 degree where they meet, so this is going to be a true statement. A height can only be drawn inside a parallelogram. Now let's take a look at our examples here. These are examples that all work. That's inside, 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 outside. So I guess the answer to that would be false. We can actually have a height on the outside. And remember, that's going to work because why? I could draw that as a deconstructed parallelogram and slide that over to make it work like that. And basically what we're doing is we're drawing it over there. Instead of having to deconstruct the whole thing or decompose the whole thing, we're just doing it by drawing a dashed line there, and with our good imaginations, sliding it over there and having a height and a base. So inside only, that would be false. A height can be drawn outside the parallelogram as long as it is drawn at a 90-degree angle to the base. Well, is that what we did here? I see a 90-degree angle with the base, so that is true. And finally, we have a base cannot be extended to meet a height. Well, that's going to be false. And we see it in that same problem right here because the base is extended out to meet a height. So that would be a false statement right there. So here we see that 5 students labeled a base B and a corresponding height H for each of these parallelograms. Are all the drawings correctly labeled, and explain how you know? Okay, let's take a look. Here we have a base and we have a height. A base and a height connect at a 90-degree angle, so that's great. Does it matter that's on top at the high point or not the bottom? It really doesn't matter. But the base is just going to be where this line connects with this line at a perpendicular or 90-degree angle. So this one's going to be okay. No problem with that. Okay? If anything, you might want to put it down there. You know, if you were drawing it on your own, you probably would draw it here and here. Just a little more comfortable for your brain to kind of go, yes, base is the bottom. But it works out just fine. It's not a big deal to put up top. On this one, here we have a height. It's coming down, it's connecting to the base, but what's missing? What's missing right there? Yep, we don't have a 90-degree angle, do we? Because it's not a 90-degree angle, this height is not going to work for us. Okay? Could you make it work in a different way? Yep, we sure could. We could get rid of the height here. We could extend the base out by drawing a height like this. Extending the base out like so. 90-degree angle, which is the equivalent of drawing a line there, right? And taking this triangle and sliding it over there. That's what could be done, but it wasn't done. Oh, and look over here, C. That's exactly what they did to C, isn't it, right? They took the height by extending the base and drawing a height and a 90-degree angle. That's a perfect way of doing it. No problem, that's great. Here, in D, we have a height. It connects to a base, 90-degree angle. We're great, in good shape there. And finally in E, we have a base and a height. Sure, they connect, but what do you notice about this? That's right, it's not a 90-degree angle. It has to be 90 degrees in order to work there. So since it's not, that one won't work either. Again, they could have, what? Extended the height, extended the base, drawn a height, and then they would have been okay. So the height has to be perpendicular to the base. That's really important to have there. Okay, let's look at activity number 3. Finding the formula for area of parallelograms. For each parallelogram, A, B, C, and D, listed here, identify a base and a corresponding height and record their lengths in the table that follows. And then find the area in the rightmost column. Alright, so we're going to figure out a base and a height and fill in our table. Alright, so for A, I'm going to go with the base being here and a height being here because I have a what? 90-degree angle. So in this case the base is 1, 2, 3, 4 and the height is 1, 2, 3, 4, 5, 6. And I can multiply those together. 4 times 6 gives me a total area of 24 square units. B. For B, I'm going to choose to decompose this one here. But really I don't need to decompose it, I'm sorry. I can draw a height right there to match a base. This becomes my height and this becomes my base. I don't need to decompose. We know how to do this now, right? So by drawing that dashed line, I form a height by forming a 90-degree angle to the base. This has then a height of 1, 2, 3. So my height is 3 and my base is 1, 2, 3, 4, 5. 5 times 3 gives me an area of 15 square units. For C, okay, same idea, right? We can go ahead and we can draw a height outside. We can extend the base of there and draw a 90-degree angle. So what's our base? 1, 2, that's our base. So our base is 2. What's our height? 1, 2, 3. And 2 times 3 gives you an area of 6 square units. And then finally D, we can extend over here, or extend that to make a 90-degree. This would probably be more my base, because it's more, yeah, it's just fine there. This would be my height, okay. I could also do it inside, right? I could go here and make that this one my base, and this my height, same idea. Here, in this case, here my base is going to be 1, 2, 3, 4, and my height is 2. 4 times 2 is 8 square units. So for any parallelogram, we take the base, multiply by the height, and it gives us our area, which is going to be BH square units. Multiply those together. Alright, pretty cool. Alright, in the next activity, it's a little bit Are You Ready for More, which you may or may not have done in class. It says, what happens to the area of parallelogram if the height doubles but the base is unchanged? What about the height triples? What if the height is 100 times the original? Well, let's look at an example real quick. Let's pretend I'm working with a rectangle that is a height of 3 and a base of 2. Okay, just as an example. In this case here, our area would be what? 3 times 2 is 6. So if I was going to double the height, what is doubling the 3? Doubling 3 becomes 6, and 6 times 2 becomes 12. So if I double it, what happens? Well, then the area doubles. So when you double the height, you double the area. Okay? What if you triple the height? Well, let's take a look. I'll erase my 6 real quick and erase my 12. Let's triple it. So what's 3 times 3? 3 times 3. Okay? Alright, that's going to be what? Any idea? The height triples. 3 times 3 is 9. Okay, and 9 times 2 is 18. So what happens to the area? Well, it's also times 3. So if you triple the height, then you triple the area. Okay? And so on and so forth. If the height is 100 times, then what are we going to find out? The area will also be 100 times larger as well. Now, in the second question, it says, what happens to the area if both the base and the height double, if both triple? So let's look at our example. So if we did, again, 3 and 2, and we doubled them up, then I would have not 3 and 2, I'd have 6 doubling and 4. So instead of having 12, I have, instead of having 6, instead of having an area of 6, I have an area of 24. So when I double it, I get 4 times as much when I double it. What happens when I triple it? Well, if I triple it, 3 times 3 is 9, 2 times 3 is 6, and that's an area of 54. So 6 times what gets you 54? That's 9 times bigger. That's a ton larger, isn't it? Right? So what happens there is it grows a lot more, doesn't it? If I do something that's 100 times the original, 100 times the original is going to be, in our case here, even larger. We're going to multiply that by another 100, which is 1, 2, 3, 4 zeros, so it'll be 10,000 times larger. That's huge. Alright, so in summary today, we can choose any of the 4 sides of the parallelogram to be a base. Both sides, both the side, the segment, and its length are called the base. So it doesn't matter, you can pick any one you want to be the base. Base, 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 doesn't matter. If we draw any perpendicular segment from a point on the base to the opposite side of the parallelogram, that segment will always have the same length. We call that value the height. So when I draw from one point to the other, perpendicular, that becomes a height. There are lots of different line segments that can be the height. I can draw this anywhere we want. As long as I'm drawing a perpendicular line, I can create a height there. So again, this shows you there's different ways of doing this, and they both work out just fine. So no matter what side you choose as the base, the area of the parallelogram is the product of that base and the height. It's the product, meaning what? We're going to multiply. So in this case, we can multiply, 4 times 6 and get 24. Here we can also multiply 4.8 times 5, a little bit different to multiply, but you still end up with 24. You can see why it's true by decomposing and rearranging the parallelograms into rectangles, right? So if I chose to do that, I could take that little chunk off here and slide it over there to make a rectangle. Over here I could take this parallelogram that's given this shape, I could take this rectangle, move it over there, and make myself a nice little shape that becomes something I can measure a little better. So that's the idea. We often use letters to stand for numbers. Okay, the base tends to be a B and the height tends to be an H, and so the area of a parallelogram is often displayed as B times H. Notice that we use this multiplication symbol of a dot, right? B times H. And that's because later on we don't want to get confused with X, that sometimes represents a missing number. So we'll start using that dot there to represent what multiplication is going to be. Alright? So later on you'll be able to prove that it's perpendicular and things like that, but for now, that's enough for there. Take a moment to work on your homework, and let's come back together to check out and see how you did. Alright, homework time for Unit 1, Lesson 5, Bases and Heights of Parallelograms. Select all parallelograms that have a correct height labeled for the given base. Alright, so to do that, it needs to come together and make that perpendicular line and have that 90-degree angle. So looking here, we can see a height and base joined together, 90-degree angle. That looks great. Here we have a height and a base, and this is not 90-degree angles, so that is not going to work. Here, we extended a line down, and we extended the base out, made a 90-degree angle. Looks great. And over here, we extended a line down for a height to extend the base to make a 90-degree angle, and that is great as well. Those are the key things, is that the base and the height come together, either inside or outside the triangle to make that height or parallelogram. So it could be there, be there. Those are all great things. Number 2, the side labeled B has been chosen as the base of this parallelogram. Draw a segment showing the height corresponding to that base. Okay, a couple ways of doing this. I can do it inside. I could draw a line right here and draw a 90-degree angle and call that my height. That's one way. I could also draw it on the outside and extend the base out this way and draw my 90-degree angle, and that would work out okay as well. So both of those would be okay, either drawing on the outside or the inside of the parallelogram. Number 3, find the area of each parallelogram. Okay, the first one's pretty straightforward. We have a length of 1, 2, 3, 4, and a height of 1, 2. 4 times 2, 4 times 2 equals 8 units squared. Over here, well, I can draw a height. I can put on the outside and draw a base. So I have a height of 2 and a base of 1, 2, 3, 4, 5. So 5 times 2 has an area of 10 square units. And then finally over here, let's call this a base, and this has a base of 2. And I'm going to draw a height on the inside this time. There's my 90-degree angle. So my height is 1, 2, 3, 4. So 2 times 4 gives me an area of 8 units squared. I could always do this on the outside, right? And go outside, outside, and which is, I'm putting that triangle over there, same thing. If the side that is 6 units long is the base of this parallelogram, what is the corresponding height? So if the side is 6 is the base, what is the height? So let's take a look here, sorry. So if this is considered to be the base, if that's the base side, then which one is the height? The height is the line that has to come down and make a 90-degree angle perpendicular to the base. So the only line that does that is this one right here, and that has a value of 4 units. That becomes our height. Number 5. Find the area of each parallelogram. Okay, this one's pretty straightforward. It has a base and it has a height, because the 90 degrees, 9 times 4 is 36, and we'll write down here centimeters squared. The next one, we have a base of 5, we have a height, because of 90-degree angles, of 4, 5 times 4 is 20, and again centimeters squared. And for C, we don't have any numbers, or do we? Oh no! So what do? We take the base, which is B, we multiply by H, and we end up with BH. That's our answer there. Number 6. Do you agree with each of the statements and explain your reasoning? Key part here is going to be explain. I'll go over whether you should agree or disagree, but you need to make sure you explain your reasoning. A parallelogram has 6 sides. Parallelogram, 6 sides. Agree, disagree? We would probably say disagree. No, because a parallelogram has what? 4 sides. That's how that works. B. Opposite sides of a parallelogram are parallel. Do you agree, disagree? Would say yes, I'd agree with that. That's part of the definition of being a parallelogram. So you can give an example. So that has to be parallel with that one, and those with that one. A parallelogram can have 1 pair or 2 pairs of parallel sides. I would say no, right? An example would be something like a trapezoid like this, right? That's parallel, but these are not, and so that's not going to be a parallelogram. So you have to both be parallel. Both sides, opposite sides, have to be parallel. All the sides of a parallelogram have the same length. Again, they could, right? So sometimes that's true, right? If you're talking about a square, it's true for a square, but in a parallelogram, a rectangle is also one. Do those all have the same length? Nope, but that works as well. So it's not really it's not a yes, it's not a no, because it can be a sometimes. But the key thing is that the opposites always have the same length. That's what's key. All angles of a parallelogram have the same measure. Okay, again, that is sometimes true. Again, looking at a square, looking at a rectangle, but if you had a parallelogram like this, not a very good parallelogram, sorry, but if you get the idea, all those angles aren't going to be the same, are they? Opposites are going to be equal, but all are not going to be equal. Okay, number 7. A square with an area of 1 square meter is decomposed into 9 identical small squares. Alright, so we have a square, like so, and it is decomposed into 9 identical squares, small squares. So that would be like taking a line like this, and this, and this, and this. Sometimes it just helps me to draw a picture to see what they're talking about, right? So the one big square becomes 9 identical ones. Each small square is decomposed into 2 identical triangles. So every small square gets decomposed into triangles. What is the area in square meters of 6 triangles? Alright, so 6 triangles. Well, 6 triangles would be right here in this case. We could look at it and go, well, that's 1, 2, 3, 4, 5, 6. So 6 triangles is that space right there, which is a 3 by 1. So we would say 3 times 1 equals 3. We're using meters as meters squared. 3 meters squared. Okay? Alright. So what is the area of 3? Oh, actually, I'm sorry. I'm looking at my things wrong. So it's not going to be 3. My mistake. So sorry. So sorry. Back it up there. So this is going to be 6 things, 6 triangles out of how many? So it's 6 triangles out of a total of, in our case here, a total of 18. Because this is all 1. So the area has to be less than 1. Keep that in mind. The area has to be less than 1. Sorry about that. got ahead of myself. So this is 6 out of 18, or actually 1/3 of a meter squared is the area. Has to be less than 1 because the whole thing is 1 and we're only doing a part of it. B, how many triangles are needed to compose a region that is 1.5 square meters? Okay, so this is a great one because to make 1 square meter out of triangles, you would need all 18 triangles. So you have to have 18 for sure, but then I also need to have that half. Well, what is half of 18? 9. So to make a shape of 1.5 square meters, how many triangles? 18 plus 9, which would be 27 triangles would be needed. Alright, and I believe that is it for the day. Sorry about that little confusion there for a second, but I hope we helped you out a little bit. Have a great day. We'll see you next time.